In geometry, a dodecahedron is any polyhedron with 12 flat faces. The most familiar dodecahedron is the regular dodecahedron, which is a Platonic solid. There are also 3 regular star dodecahedra, which are constructed as stellations of the convex form. All of these have icosahedral symmetry, order 120. The Pyrite is an irregular pentagonal dodecahedron, having the same topology as the regular one but pyritohedral symmetry, while the tetratoid has tetrahedral symmetry. The rhombic dodecahedron, seen as a limiting case of the pyritohedron, has octahedral symmetry. The elongated dodecahedron and trapezo-rhombic dodecahedron variations, along with the rhombic dodecahedra, are space-filling. There are a large number of other dodecahedra. Pentagonal dodecahedron. The convex regular dodecahedron is one of the 5 regular Platonic solids and can be represented by its Schläfler symbol 5,3. The dual polyhedron is the regular icosahedron 3,5, having 5 equilateral triangles around each vertex. In crystallography, 2 important dodecahedra can occur as crystal forms in some symmetry classes of the cubic crystal system that are topologically equivalent to the regular dodecahedron but less symmetrical. The pyritohedron with pyritohedral symmetry, and the tetratoid with tetrahedral symmetry. Pyritohedron. A pyritohedron is a dodecahedron with pyritohedral symmetry. Like the regular dodecahedron, it has 12 identical pentagonal faces, with 3 meeting in each of the 20 vertices. However, the pentagons are not constrained to be regular, and the underlying atomic arrangement has no true 5-fold symmetry axis. Its 30 edges are divided into 2 sets, containing 24 and 6 edges of the same length. The only axes of rotational symmetry are 3 mutually perpendicular 2-fold axes and 4 3-fold axes. Although regular dodecahedra do not exist in crystals, the pyritohedron form occurs in the crystals of the mineral pyrite, and it may be an inspiration for the discovery of the regular Platonic solid form. Crystal pyrite. Its name comes from one of the 2 common crystal habits shown by pyrite, the other one being the cube. Cartesian coordinates. The coordinates of the 8 vertices of the original cube are. The coordinates of the 12 vertices of the cross-edges are plus or minus 0, 0, plus or minus, where h is the height of the wedge-shaped roof above the faces of the cube. When h equals 1, the 6 cross-edges degenerate to points and a rhombic dodecahedron is formed. When h equals 0, the cross-edges are absorbed in the facets of the cube, and the pyritohedron reduces to a cube. When h equals square root 5 minus 1/2, the inverse of the golden ratio, the result is a regular dodecahedron. A reflected pyritohedron is made by swapping the non-zero coordinates above. The 2 pyritohedra can be superimposed to give the compound of 2 dodecahedra as seen in the image here. Geometric freedom. The pyritohedron has a geometric degree of freedom with limiting cases of a cubic convex hull at one limit of collinear edges, and a rhombic dodecahedron as the other limit is 6 edges are degenerated to length 0. The regular dodecahedron represents a special intermediate case where all edges and angles are equal. Tetratoid. A tetratoid is a dodecahedron with chiral tetrahedral symmetry. Like the regular dodecahedron, it has 12 identical pentagonal faces, with 3 meeting in each of the 20 vertices. However, the pentagons are not regular and the figure has no 5-fold symmetry axis. Although regular dodecahedra do not exist in crystals, the tetratoid form occurs in the crystals. The name tetratoid comes from the Greek root for 1/4 because it has 1/4 of full octahedral symmetry, and half that of pyritohedral symmetry. The mineral cobaltite can have this symmetry form. Its topology can be as a cube with square faces bisected into 2 rectangles like the pyritohedron, and then the bisection lines are slanted, retaining 3-fold rotation at the 8 corners. Cartesian coordinates to generate a tetrahedroid pentagon under tetrahedral symmetry. Choose numbers. Chapter 0 A BC. Calculate. N equals A2C minus BC2, D1 equals A2 minus AB plus B2 plus AC minus 2BC, D2 equals A2 plus AB plus B2 minus AC minus 2BC. If n d1 d2 0, then the following are vertices of a tetrahedroid pentagon. Variations. It can be seen as a tetrahedron, with edges divided into 3 segments, along with a center point of each triangular face. In Conway polyhedron notation it can be seen as GT, a gyrotetrahedron. Rhombic dodecahedron. The rhombic dodecahedron is a ionahedron with 12 rhombic faces and octahedral symmetry. It is dual to the quasi-regular cube octahedron and occurs in nature as a crystal form. The rhombic dodecahedron packs together to fill space. The rhombic dodecahedron can be seen as a degenerate pyritehedron where the 6 special edges have been reduced to 0 length, reducing the pentagons into rhombic faces. The rhombic dodecahedron has several stellations, the first of which is also a parallelahedral space filler. Another important rhombic dodecahedron has 12 faces congruent to those of the rhombic triacontahedron, i.e., the diagonals are in the ratio of the golden ratio. It is also a ionahedron and was described by Bielinski in 1960. This figure is another space filler, and can also occur in non-periodic space fillings along with the rhombic triacontahedron, the rhombic icosahedron and rhombic hexahedra. Other dodecahedra. There are 6,384,634 topologically distinct convex dodecahedra, excluding mirror images, having at least 8 vertices. Topologically distinct dodecahedra are uniform polyhedra. Decagonal prism 10 squares, 2 decagons, D10H symmetry, order 40. Pentagonal antiprism 10 equilateral triangles, 2 pentagons, D5D symmetry, order 20. Johnson solids. Pentagonal cupola 5 triangles, 5 squares, 1 pentagon, 1 decagon, C5V symmetry, order 10. Snub dysphenoid 12 triangles, D2D. Order 8 elongated square dipyramidate triangles and 4 squares, D4H symmetry, order 16. Metaba diminished icosahedron 10 triangles and 2 pentagons, C2V symmetry, order 4. Congruent irregular faced. Hexagonal bipyramid 12 isosceles triangles, dual of hexagonal prism, D6H symmetry, order 24. Hexagonal trapezohedron 12 kites, dual of hexagonal antiprism, D6D symmetry, order 24. Triacus tetrahedron 12 isosceles triangles, dual of truncated tetrahedron, TD symmetry, order 24. Other less regular faced. Hendecagonal pyramid 11 isosceles triangles and 1 regular hendecagon, C11V, order 11. Trapezo-rhombic dodecahedron 6 rhombi, 6 trapezoids, dual of triangular orthobicupola, D3H symmetry, order 12. Rhombi-hexagonal dodecahedron or elongated dodecahedron 8 rhombi and 4 equilateral hexagons, D4H symmetry, order 16. Truncated pentagonal trapezohedron, D5D, order 20, topologically equivalent to regular dodecahedron.